All right, so let me start. Okay, so we are here. What we learned, in the previous discussion was about the principle of superposition and how it should work. Where we have to be very careful when we talk about superposition, that this is an experimental fact, etc. We learned in the last lecture. Okay, so I'm just going to revise a little bit in few minutes, and then we'll go for the new things which I planned for today. So we begin with considering very special case of electrostatics, where we think that our source charges should be stationary, though the test charge can be movable. And there we defined the Coulomb's law, where we talked about that how Coulomb's law basically is proportional to the product of two charges and inversely proportional to the distance square. And we defined epsilon naught as well as the permittivity of free space. Okay, and therefore we solved one problem where we talked about that if 12 equal charges are there with equal magnitude q, which are situated at the corners of the regular 12-sided polygon. So we calculated what is the net force on the test charge q at the center, and by symmetry we say that it is 0, right? And then after we also by that symmetry requirement we said that if one of the 12 q's was removed, then what could be the force and what could be the reason for that. Okay, so we said that that force is going to give by the expression here, and then we gave an explanation that because this is just a clock, so it is just like something like this. So by symmetry requirement we can suppose for the first part of this question that all the forces are going to be cancelled, like the charge which is sitting at 12 can be cancelled by charge at 6, similarly 1, 7, similarly 2 and 8, etc. Okay, and if one of the charges, let's say at 6 o'clock, is removed, then the force is going to be in the direction of this from 12 to 6, and this is the magnitude is given as this. So one of the explanation we gave by symmetry in the last lecture. Okay, but also since we learned about the superposition, so what we can say here that by superposition principle, if you apply the forces, and now you are an expert on that because in the last lecture we discussed that how to determine the directions and how the components is going to be calculated depending on the our reference frame. And accordingly we can see that if I wanted to calculate this force, then we can apply the superposition principle, and then after we can so let's suppose our x-axis is this and y-axis is this. So depending on that we can always have for example one of the force is acting something like in this direction. Okay, then we can find the component of this force, like the vertical and the horizontal, and therefore we can calculate similarly for all the charges. And when we sum up all those charges, the first question is going to give us the 0 net force, and similarly for the second problem we can explain the same thing. So this is very important in a sense that the question which I gave you as an homework in the last discussion. So if you have now 13 equal charges which are placed at the corners of a regular 13-sided polygon, so again what is the force? So by having the superposition principle in our mind, we can calculate it just like a 0. Okay, so here if the same question was repeated, like if one of the 13 Qs is removed, what is the force on Q? So the force will be same as we calculated in a previous example, and the explanation should not be symmetry. Rather, we can say that this is because of the superposition principle. So that's why the superposition is very important concept, where one has to have this explanation, or you can say in a very general sense, one should talk about superposition and then calculate everything correctly. Okay. So are there any questions till now, or is it fine to everyone? So your answer matches with this, right? I gave you this as an homework. Anyone?
No question, sir.
Okay, good. So if you have solved this question, which I gave as an homework, your answer should match like this. Okay. Very good. So then after we defined the electric field, where we talked about all the superposition principles, and then electric field as defined as sum of all the charges of the ratio of some of the charges divided by the their distances according to the coordinate system what we are considering. So this is a square of this distance, and etc. Okay. So, but what we did here, this is for the discrete charges. Okay. So the charges are, just like placed as a source point, and these are like different magnitudes, Q1, Q2, Q3, etc. Okay. But we discussed this as an example then after, and we checked that how these formulas can be calculated, and we found something like this. Okay, so I'm just skipping that part, and thereafter we had solved a different problem where in the last problem there was this Q, and this Q was positive but equal in magnitude. Then in this question it was said that if you have a charge to be opposite with the equal magnitude, then how the electric field is going to work. I mean, the resultant for electric field should be. So we found that this is going to be like horizontal component, comparing to the previous one where we had a vertical component as the resultant electric field. And then after, we calculated these electric fields, and this question, which I again left. So this is the answer. So here you can see our resultant electric field is given by this expression. And when we consider Z is too large comparing to D, then this is going to return in terms of electric field, something like this. Okay. So then after, this is just a condition for the dipole, which one has to, which we will actually discuss later on, that how dipole actually works. And if I set, for example, D equal to 0 here, then the electric field is going to be 0. And the reason is very clear, because you can understand that if this distance is 0, what that means, that these two charges are very close to each other, and the total charge is going to be summed to be 0. Okay, because Q minus Q is equal to 0, and therefore electric field is going to be 0. This is very natural. Now I left the thing, and I'm going to discuss this today about the continuous charge distribution, where we talk about line charges, surface charges, and volume charges. So let's move one by one according to the definitions, and then after we will solve some of the problems, and let's see, I mean, so how far we can go. Okay, and if you have any question, please interrupt me. Okay, so I'm not going to ask again and again, and we'll discuss then. So far we learned, that's why I revised it, so that we can have an understanding that for discrete distribution of charges, this sum is given like this. Okay, so it was just like the sum of all the charges divided by Ri square, and obviously the directions are going to be very important, and therefore the electric field is given as sum of all those things. Okay, so this C is a summation sign. Okay, but when you have a continuous distribution of charge, which I just showed, then this should be replaced. That means the sum should be replaced by the integration. Okay, and then the definition is going to be changed something like this. So ER is equal to 1 over 4 pi epsilon naught integral of 1 over r square, r cap is the direction, times dq. So dq is this charge of continuous distribution. Okay, and now this contribution distribution, which we just learned, that this could be a line charge, this could be a surface charge, or this could be a volume charge. Okay, so what that means, so if the charge is spread out along a line, okay, just like this, and it is given that charge per unit length is given as lambda. Okay, so this is just a notation, and this convention is actually used in almost all the books. So we have to follow the same convention. And as the name suggests, this is charge per unit length. That means lambda is defined as coulomb per unit, whatever length unit you say. For example, meter. So coulomb per meter. Okay. So therefore, this dq for line charge is defined as lambda times dl prime. Okay, so this is again a convention where dl prime is an element of the length along the line, which you can see in this figure. Okay, so this is the continuous distribution of line charge. So charge is basically spread out throughout the wire. Okay, you can assume that a wire as a straight line. Okay, so this is completely spread out, and if charge per unit length lambda is given, then you can always calculate an element of this line of length dl prime, and the effect of this at some point, if you wanted to calculate electric field at some point p, and the distance is given as r vector, then this dq is going to defined as lambda times dl prime, and then we can apply this formula to calculate the electric field at p, because this distance is r is known to us. So what we have to do, basically we have to just replace this dq here as lambda times dl prime. Okay, and then integrate over the the limits which we have. I mean, in the problem, obviously this limit is going to give given in the problem. Okay, so this is the definition of line charge. Okay, then after we are going to discuss actually a lot of problem on this today, and maybe if time allows, I will move towards the surface. Otherwise, in the next next session, I will discuss some of the problems related to the surface charge and volume charge. But let's clarify the definitions. So now the situation could be like this was the one-dimensional object, right? But yeah.
Sir, can we, instead of dl prime or dA prime, can we use only dl or dA?
Yeah, sure. It is just a convention,
Okay.
Since I'm following one book, so I told you that, in Griffith, they generally used prime, so I use it. But overall, when we do the numerical problem, we can always use DL. Okay, this is just a convention. Very good.
Thank you.
So similarly, when charge is smeared over a surface, so if it is smeared over a surface like this, and our charge per unit area, that means coulomb per meter square, is given, then this dq should be replaced by sigma times dA prime or dA, as we already spoke about. And then accordingly, we can calculate the electric field at some point P. with a distance given as r from this dA prime. Okay. Similarly, following the same convention, if the charge fills a volume, okay, something like this, you can see in this figure, and the charge per unit volume is given as rho, then dq can be written as rho times d tau prime, where d tau is the element of the volume. So you can assume this dA. So here it is very clear that obviously this is one length, then it's fine. Okay, but if you have a two-dimensional surface, then you need to find that what dA means. Okay, you have to have a something like, let's suppose you have a square board or something like this, then obviously this dA prime is given as, you know, length times the breadth, okay, or the width, whatever you wanted to have. But if it is a volume, then what this means you have to have a three dimension. Okay, so this d tau or d tau prime is going to give us dx times dy times dz. Okay, so we're going to see this. We are going to see this, and we will then, you know, when we solve some of the numerical problem, then we're going to digest this concept very easily. And for that also, I mean, the sum of the coordinate system is going to help us, and how this is going to happen. Probably today I will not able to come up to this point. And in the next session, maybe I will give you more example on these two things altogether. So, but in between, we can practice a lot over the concept which is dependent on something like, you know, the line charge. Okay, so overall, what we can do, that dq should be lambda times dl for line charge, and this is equivalent to a surface charge if it is sigma times dA, and then it is equivalent to, you know, rho times d tau if we talk about the volume. Okay, so overall this dq is defined in these three kind of dimensions according to this. And as I said again, so let me repeat it again. So if it is one dimension, for example, so this could be lambda times dx, this could be lambda times dx times dy, and this could be lambda times dx times dy times dz. Okay, so this is going to be more you know, helpful to understand overall concept about the electric field. And by using this, now we can define our electric field for these three configurations. Okay, and this is simply given by, so what we do, generally we replace this dq by lambda dl prime for line charge. It is given as, so you can see here, so lambda is a function of this r prime, and we're going to see that how this r prime is basically defined in a configuration space. And therefore, you know, this is just the replacement of this dq to lambda dl prime. Okay, so you can see here very clearly, and this is going to be, you know, you don't have to remember. Basically, if you know this convention, then you know, and you know this formula, then obviously you have to substitute this, and you're going to find these expression very easily. So similarly for a surface charge, and similarly for a volume charge, you have to have this. So what this means here, again, let me repeat, that this integral is over one dimensional space. Okay, so this is just like dx. Okay, so only one dimension. However, for this you have to have a two dimension, because you have to integrate it over dx and dy. Or maybe if you reduce one variable in terms of another variable, then obviously you can have the single integral to be evaluated. Similarly, here you have a three integral involved, dx, dy, dz, and you should know with what limit is there. And if again the constraints are given, then you can reduce it into two dimension or one dimension accordingly. Okay, and we're going to see these examples, you know, very soon, and trying to get expertise on that. Okay, so this is fine with our definition. So I will not discuss too many of such mathematical formalism and the concepts. So let's target to solve one of the problem, which is very important for all of your exams, or, you know, whatever competitions you are writing. So it is given a line segment, which you can see here, okay, of length 2L, and it carries a uniform line charge lambda. Now we have to find an electric field at distance z above the midpoint of the straight line segment. Okay, so this is a straight line. Okay, so this is given with a length of 2L, and it says at the midpoint of a straight line. So midpoint will be somewhere here. So if I say this is 2L and this is and we say this is an origin, then we can say this is plus L and this is minus L. Okay, so let me write it here so that it could be more clear. So what according to this, our convention, we can say that this is 0. So from here to here, this is L, and from here to here, you want to have minus L. Okay, this is very important because you just see that we are going to integrate. So these limits are necessary to understand. Okay, so to start with, what we can do either way is that, which I will left to you. I will just give you some hint which you can always calculate, but I will do it in a more generalized manner. To how to approach this kind of problem, so that you should have a bigger picture of this problem. But the problem which we first did for the discrete charge distribution, where we have a q here and q here placed at d over 2. So for this, the same problem, if you just apply, because you see, these are like a similar thing. Okay, in what case? In the case if I just replace d over 2 as x and q as lambda dx and integrate x from 0 to L, then we're going to get the solution. Okay, and this problem you have already done. So try to use this formula and let's see that if it is going to match with the generalized formula. Okay, so just take this as an homework for your gain of knowledge and everything. So let me use the very generalized form which we just discussed. So we know that for a line charge, electric field is given as 1 over 4 pi epsilon naught integral of lambda divided by r square r cap dl prime. Okay, so what we need to find here, lambda is given, r we need to find, okay, and dl obviously we need to consider, which is here considered as the dx. So let's first of all do the formalism. Okay, so what are the things which we can assume here? So let's suppose this is a r vector because we need to find the field some point here. So this is defined as r vector as z times, z is the magnitude from this point O to point P, and z cap is the direction, which is very easy to understand. Now r prime is in this direction, okay, because here is the element of charge we are considering. Okay, so this r prime is, let's suppose at x distance we consider an element of charge with a length dx, which is very infinitesimal. Okay, it is very small difference. So this dl prime is basically our dx. So this is dx, and this r prime is x times x cap, because this is a vectorial quantity, distance. So we have to consider that in the x direction, x cap is the direction, and in the z direction, we take as a z cap. Okay, so this is our formalism. Again, what we want here. So according to this is z. Now, by using this formalism, we can also calculate this distance, because this is needed here in this formula. Okay, so first of all, let's calculate this r vector. So this r vector in terms of r and r prime can be written as r minus r prime, and then you have to substitute simply the value of r vector and r prime. Okay, so once you substitute, you can have this r vector as z times z cap minus x times x cap. Okay, and using the Pythagoras theorem, you can always calculate R as equal to root of Z square plus X square, or you also know how to calculate the magnitude of any vector. So by using that, you can also calculate this. Okay. Similarly, you need to find the unit vector in this direction. So unit vector is going to give us, as we know by definition, that any unit vector is the vector divided by the magnitude of that vector. Okay. So this R cap is equal to R vector divided by R. And R and R, so you just substitute it here. This is we going to use for calculating the electric field at point P. Okay, so this is one thing. Another thing which I already showed, that when we going to integrate it, we need to have the limits. So here, according to our convention, the limits is basically minus L to L. Okay, so these are some of the information which basically needed to calculate the problem here. So let's move with this information. So this is all which I showed in the last slide. So now let's substitute it. Okay. So once we substitute this, so the limit is minus L to L. Okay. Lambda is given. So lambda is given here. R square, we know that this is given as Z square plus X square, and R cap, we calculated Z cap minus X cap divided by root Z square plus X square. DL prime is dx, so this is dx. Okay, so this is simple substitution. All right. So if you go like this convention and slowly move accordingly, then what we need to do, it is just like now integration over X. Okay. So the next step will be like this. So what we can do, because Z is just a constant, our variable is X, right? We have to, so that's why under the integration sign, we must have X inside. Okay, so let's fragment these two parts together. So Z cap, because this is a constant, constant in a sense that we are integrating over X only. Okay, so integrate over minus L to L, and this is Z square plus X square times root of Z square plus X square. So we can have this over 3 over 2. You can combine and then integrate over dx. Similarly, the second term, which is minus xx. Now x is the variable here, so we have to have just x cap outside, and the integration should go for this x over Z square plus X square 3 over 2 dx. And by integration itself, so I'm not going into the detail of integration, how to do this integration, but there are various ways of doing this kind of integration. So by using that, you integrate it, and you will find that this integral is given by x divided by Z square times Z square root of Z square plus X square, and the limit is minus L to L. Similarly, this integration is given as minus 1 over root of Z square plus X square, and again we have to put the integration limit, so which is minus L to L. And once you put all the values, you're going to get the expression like this. So this is going to give us 1 over 4 pi epsilon naught 2 lambda L divided by Z times root of Z square plus L square Z. Okay. So up to this point, I hope there is no confusion. But if you have any question or something, you can obviously ask. Okay. Because, I gave this in detail of this problem, but later on, I'm not going to give you the details. Rather, you have to work out by yourself. I will just give you some hints, and, you have to work out on other such kind of problems. Okay. So,
Sir,
yes.
Sir, can we multiply right side of E by 2 and integrate from 0 to L?
Of course. See, the point is that, yeah, you can reduce this integral if it is symmetric. Okay. And you have the factor of 2. Rather than, I would also say, this is my convention, from minus L to L I have taken, but you can take it as just like 0 to 2L. in this diagram, to solve this, since we have to find this from the midpoint, so I took this as an origin, and then I say that, okay, I have to integrate from minus L to L, okay? But you may choose your origin like this, and you can integrate from 0 to 2L, okay? And if it is symmetric, then obviously you can use the integration formula where you can have 2 times that, form. But for this convention, I can't do that, okay? For this convention, I can't do that. You can reduce it in whatever form you want, but depending on what limit you want it to have, okay? Is it clear?
Okay, sir. Okay, sir.
Yeah.
Thank you.
Yeah. Because integration formula, I mean, this is just a fundamental laws of integrations, that where you have to use two times integral of 0 to L, so just use that and see, are you going to apply, are you able to apply it here or not? Okay, so this is just a symmetric or asymmetric function you are dealing with. All right, very good. So again, as we discussed in the last examples, that we always try to verify things in some limits, okay? So let's suppose we have, points where we wanted to have, like Z is very far from the line charge, okay? So if it is, in this case, what you wanted to have, you have to, just take the ratio. For example, you can take the ratio here and take out Z outside. So Z is going to be outside because it is a square, and it is, if it come out from the square root, then it is going to be Z and multiplied with this Z. So this is going to be Z square, and this is going to be 1 plus L square by Z square. And Z is too large, so we can neglect this term, and therefore this is going to be 1, okay? So in this such situation, you're going to get electric field simply like, so this act as a single charge, you can see very beautiful expression here. And this 2 lambda L is basically working as a charge, okay? So by having this, limit, okay? So these are some of the salient points which one should discuss once you use this kind of formula. Also, one could ask that if L is infinity, that means your line charge is very, very large, okay? And you wanted to see the electric charge very near to, or you can say you have, for example, you have, like this infinite line, and you wanted to see electric field very near to that point, okay? So for this point, basically this line charge is, expected to be infinite, okay? So in that situation, again, you can use L to be infinity and try to see that how this is going to work. So what you can do for this problem, you can always take this out, okay? And into the integral sign, just by dividing it. So if you divide this expression, the numerator by L and denominator by L, then you can substitute L square inside. Or another way of doing this is you can take that's the only way. So you have to do this, and then you will see that if L is going to be infinity, this term is going to give you 0, and this is going to be 1. So you left with 1 over 4 pi epsilon naught 2 lambda over Z, okay? So this is another very interesting example where you can see that now electric field is proportional to simply the vertical distance Z, okay, which is not the case here. But you can see the dimensions are equal. Dimensions should be equal. So here one of the L dimension is going to be cancelled out with the dimension of Z. So we are consistent with the formula of electric field. Similarly, you can see that the dimensions are also well defined here. Okay, so these are very salient point that one has to take care once solve any such kind of problem. And I would suggest that maybe in the competitive exam you can use such kind of things very frequently, especially if it is some kind of multiple choice questions. You can answer such kind of question very quickly. Okay, so I hope that problem is clear. So now another problem can be like this. Okay, so let's suppose you have something like this wire. Okay, and you need to find electric field at some point P near to one of the edges of this wire. Okay, which is and the distance is given as Z. So how are you going to do this? Okay, so obviously we don't have time because it will take a lot of time. If I gave you time, it will take maybe 5-10 minutes to solve. So if such kind of problem is there, you can always use the previous problem which I just discussed, and then you can find the electric field very easily. So again, what you have to do, you can just take a convention. Let's suppose this is x-axis, this is your z-axis, and then this is r, and therefore you can take one element here of dx length, but now integration will be go from 0 to L. Okay, and accordingly we're going to solve the problem. So this is one of the things which you can always use. However, you can always represent this in terms of cos theta, and how this comes about, because the unit vector direction can be calculated something like cos theta, which is very easy to understand. And in one of the problem I showed you that what this cos theta means, why it came into the picture. Okay, so please use these. I'm just giving you expressions and answers. Okay, and this should be your answer. And if you don't find this, or is there any difficulty, you can always ask in the next session. But I would suggest that please solve such kind of problem, and your answer should match with this accordingly. Okay, another such kind of problem could be complicated, and you have a situation like this. So you have a rectangular wire. Okay, so in a rectangular shape, something like this. Okay, and let's suppose the length is given as A. So this is A, this is A, this is A. Okay, then how you're going to calculate the electric field at some midpoint of this square? I mean, the distance is basically from the midpoint, and it is given as Z. Okay, so in that situation, how you're going to find the electric field? So I'm just giving you the hint here, and try to solve this problem. So what we have to do, first of all, again, using the previous example which I just gave, you can suppose that this is one of the wires. So because of this wire, what could be the electric field at point P? And then what you need to do, you need to sum up all the forces, all the electric field, and where is my cursor? Okay, all the electric field, and then you can have something like the component, which is, I mean, you need to see this picture. If you remember that if we have two equal and opposite charge, and we wanted to calculate the electric field, then you saw that the resultant was the vertical electric field which we got. So now you have to see that because of this, what are the directions of electric field at point P, and which direction is going to cancel because of this part of wire. And similarly, you have to see this part and this part. Okay, so this is just a hint which you need to apply. And then after, also you can use in this expression itself, just substitute L equal to A over 2, because this is at the midpoint. Okay, so in this problem we have L, And z is obviously you can calculate then. Z is going to give z square plus a over 2 whole square root of this, which is distance from center of the edge to P. And therefore field of one edge, like this one edge, is going to be given by E1 equal to 1 over 4 pi epsilon naught root over lambda a divided by this expression. Okay, so you can do this by substituting these values in this expression. Okay, and therefore what you need to do, you need to obviously take all the component there, all the 4 parts, and then you should have this electric field accordingly. Okay, so I'm just giving you the hint of these problems rather than going into the details of this, because it is now correlated from one example to another example. So please try to solve this problem. Another situation can occur. So you see, these are very correlated problems. Okay, that instead of this rectangle, if I make it like a circle, okay, so something like this. Okay, so let me make it a circle with radius r. So what could be the field at point P? Again, you need to consider here, it is very essential to understand by noting 2 points, rather 1 point actually, that you can see that, let's suppose if one charge is here, okay, and one opposite charge is sitting here. It is just like the problem which I just discussed about the clocks and all those things. Okay, so you can see that electric field due to this is going to be like in this direction, and due to this charge, electric field is going to be in this direction. So you can calculate that, okay, the resultant electric field will be in the vertical direction only. Okay, so similarly, there are various points you can choose, and symmetrically there is existence of another charge opposite to each other. So what could be the direction of electric field due to this circular wire? Okay, so you can do this very easily. So what you have to do, you have to again use the formula which we just used before. So this is given as 1 over 4 pi epsilon naught integral of lambda dl by r square cos theta z. So cos theta is defined according to our convention. So you can substitute that value, and then electric field can be, because this is going to be vertical direction always. Okay, because horizontal directions are always going to be cancelled, because there are equal charges in the opposite direction, like in a symmetric way, as we discussed about the 12 charges we talked about. And then after, we also solved one problem where we had 2 equal charges, and we found that the electric field is basically given as the vertical component only. So you can see here that the vertical component is given by z cap. Okay, and to just give you the hint here, when you integrate some element dl, so this is going to give you the circumference, right? Because you can start with 0, and then overall you can have the 2 pi r. So you can simply substitute 2 pi r, you're going to get the answer very quickly. Okay, so these are the very correlated problem. Once you solve one of the problem, you're going to solve another one accordingly. Okay, so but yeah, if you have any doubt till now, you are open to ask any question. Anything, or you happy to work out over weekend? Okay, yeah. So I suppose that please work out on these things by yourself, and if there is any problem, then let me know. Okay, so next problem I will discuss not today, because already we have past 45 minutes. So another problem, we're going to generalize this problem, and maybe I would suppose that you can also try to look by yourself that this was the wire actually. Yeah, so this was the wire, which is like a circular wire, and this was act as a one-dimensional object with where lambda was given with the length with a charge per unit length. Okay, but let's suppose now this is a plate, something like this, okay, with distance r, and we wanted to find the electric field at point P with this given configuration. So how we can generalize this formula in terms of sigma? Let's suppose sigma is given here. Okay, let's suppose sigma is given as charge per unit length. Okay, so please try to work out on this. And this is a little bit of complicated problem. So for this, actually, I wanted to just give you a prelude of this, that here we wanted to use a coordinate transformation where we will not talk in terms of Cartesian coordinate system. Maybe we're going to transform it into the spherical polar coordinate, or if problem allows you, you can always use the coordinate system of the in the Cartesian coordinate system, and you can also solve this problem. So we can see this problem by considering the concept of charge distributed in a volume. Okay, so with this, let me end today's session, and if you have any question, please ask. Anything?
Excuse me, sir.
Yes.
Sir, actually, I missed one slide. Can you just show the slides from the beginning, or you will have any problem?
No. Let me just show you. Rather, let me minimize this, and I'll show you that one. And let me erase because this is not needed. So if I keep minimize this, and then maybe you can. So which slide you wanted to see? Actually, I started somewhere with the revision, and please stop me, okay? So this was just a revision where I just discuss things. So I'm going a little bit faster, but if you stop me. So I started basically today's session with the discussion like this. Yeah.
Excuse me.
Yeah.
Yes, it's the last one.
The last one.
Yes, sir.
Okay, this one. Okay. Yeah. So here.
Yes.
Yeah. So here actually, this was a simple concept which in the last session also we discussed, that how we going to define the line charge, surface charge, volume charge, etc. Okay. So in general, if we have some continuous charge distribution. Okay. That's fine. So is this all?
So can you go ahead, sir?
Yeah.
Sir, can you go ahead with the slides?
Yeah, sure. So then, yeah, we discuss this. Is it okay?
Yes, sir.
Okay. Then we discussed this slide.